Math 1314, Tyler Junior College, Section 1.6, Other Types of Equations, Quadratic-Like Equations continued. In the previous video, we developed a technique for solving what we dubbed quadratic-like equations. Just a reminder, those are equations with two terms with matching bases and one power is twice the other. For example, x to the fourth power minus 5x to the second power minus 36. Two of the terms have matching bases, base being a part that has an exponent. In this case, the matching bases are x, but one power is twice the other, or is twice 2. Since this meets the criteria for being a quadratic-like equation, we can solve it using a substitution. Just a reminder, for the substitution, we're going to let u be the lesser of the two powers, or the variable of your choice. The default variable here tends to be u for whatever reason, but by letting u be the lesser of the two powers, then u squared is the greater of the two powers. So how can we solve this one? Well, it is quadratic-like as we've already established, so we're going to let u be the lesser of the two powers. The lesser power is 2, and it is a power on an x. As a consequence of that decision, if we squared both sides of this substitution, we would get u squared equals x to the fourth. That's why u squared will always be u squared will always be the greater power, because squaring the smaller power doubles it. As a consequence of these substitutions, x to the fourth is going to get replaced with u squared, and x to the second is going to get replaced with u, and the rest of the equation remains intact. So now what? You can come on if you want. If you want to be on video, walk past this line.
I do not want to.
Okay. I'll be down in a moment. Okay. So, we have a visitor. So, now this quadratic-like equation really is a quadratic equation, and we can solve it as such. Feel free to get out the quadratic formula. While you're setting it up, I'll be done because this guy's going to factor. So what two numbers add to give -5 and multiply to give -36? Probably some flavor of 9 and 4. For the sum to be negative, the larger number should be negative, but for the product to be positive, the number should be opposite sign. Yay, it's factored and equal to 0. That's a good place to be. Set each factor equal to 0. And solve. And we get u equals 9 and u equals -4. But don't get excited. We weren't asked what u equals at the beginning. The implication is what is x equals, and we don't know that yet. But remember that a substitution is temporary. Thank you, u. I appreciate you making the problem easy. Get out. Give me my x squared back. So undo the substitution. U is equal to x squared. So now we have x squared equals 9. That's easy to solve. And we have x squared equals -4. That's also easy to solve. Hey, look, two baby quadratic equations. They only have one x term, so we can use square roots. The squared term is already isolated, so it's time to break out the square roots. Square root of x squared equals the square root of 9. The square root of x squared equals the square root of -4. And remember, the reason for that move is to cancel the square. But don't forget that the square root property says that we have to use plus minus. So we get x equals plus minus 3. And over here, we get x equals, oh goody, a square root of a negative. But at this point, it shouldn't be anything, especially the square root of -4. That's just 2i. Is there another way to solve this without substitution? Actually, yes, but we won't learn that until we get to chapter 3. So, quadratic-like equations. Here's what they are, and here's how to attack them.